Hello everyone, it's Phil here from 360 Maths, and today we have a really nice sequence to have a look at. The question here says, what is the next term in this look and say sequence? So the first term is 1, second term is 1, 1, third term is 2, 1, next term is 1, 2, 1, 1, and then the last fifth term here you've got 1, 1, 1, 2, 2, 1. So the question is, what comes next? So I'm going to give you a minute or so to have a think about this, and then we will get together and we'll discuss the problem a little bit further. Okay, so the sequence started with the number 1. That is often known as the seed for the sequence. Now what we need to do next to construct the next term is to look and say what we've just written. So what I've just written down is 1, 1. Okay, now let's look at what I've just written down there. I've written down 2 1s. What have I just written down there? I've written down 1, 2 and 1, 1. And then we can continue on in this way, and I've got 1, 1, 1, 2 and 2 1s. So the answer to this problem will be the next line. Now here you can see we've got 3 1s, 2 2s and 1 1. So that is the answer you were looking for. Okay, very well done if you managed to get that. Let's just push the sequence on a little bit further to see how it develops. So the next term will be 1, 3. Then we have 1, 1. Then we have 2 2s. And then we have 2, 1. Okay, so let's play around with this and see what happens if we change the seed. So let's look at a seed of 2. So the next term will be, we see 1, 2. Then we have 1, 1, 1, 2. And we have 3 1s, 1, 2. 1, 3, 2, 1, 1, 2. 1, 1, 1, 3, 1, 2, 2, 1, 1, 2. And if we change the seed to a 3, we would have 3, 1, 3, 1, 1, 1, 3, 3, 1, 1, 3, 1, 3, 2, 1, 1, 3, 1, 1, 1, 3, 1, 2, 2, 1, 1, 3, etc. Okay, and now let's change the seed to 4. So we'd have 4, 1, 4, 1, 1, 1, 4, 3, 1, 1, 4, 1, 3, 2, 1, 1, 4, 1, 1, 1, 3, 1, 2, 2, 1, 1, 4, etc. Just take a couple of minutes to have a look at those sequences and see what sort of patterns you can see. So you might have noticed a few things there. Did you notice that the seed is always the last term of the sequence? The seed is always the last term of the sequence. Okay, and did you also notice that when the seed is 2 or greater, that this part of the sequence is just repeated for each one? Also, did you notice that if you ignore the seed, ignore the first term, the only digits that appear are the digits 1, 2 and 3. And another thing you might have noticed is that the sequence 3, 3, 3 never appears. So the fact that the sequence 3, 3, 3 never occurs is a really good example of proof by contradiction. So let's just have a quick look at that. The way it works is if you assume that 3, 3, 3 does exist in this sequence, then that means that the previous term must have read this, 3 3s and 3 of something else. Well, if you've got 3 3s and 3s of something else, you've contradicted the previous statement that 333 doesn't occur. So that's a proof by contradiction that 333 can never spring up in these sequences. Another point of interest is to look at the length of each term in the sequence. So here you can see the fourth term has 1, 2, 3, 4 digits, and the next term has 1, 2, 3, 4, 5, 6 digits, and you can continue down. So you get another sequence which is formed from the original sequence. Now this is something that John Conway did, the English mathematician, and he analysed this second sequence in particular by looking at the ratio of consecutive terms. So if you look at 2 divided by 1, you get the answer ratio of 2. 2 divided by 2 gives you 1. 4 divided by 2 gives you 2. 6 divided by 4 gives you 1.5, etc. And then if you look at the ratios, what he discovered was that they are converging to a constant. This constant is known as Conway's constant and is equal to 1.3035 ... So what that means is that each progressive term in the sequence is increasing in length by about 30%, just over 30%. So that's quite amazing in itself, but also of interest is that that constant is a solution to a polynomial of order 71. So this is the polynomial. Now if you solve this using a computer or some computer software, you can see all of the solutions in the complex plane. So here are all of those solutions. Now the one that we're interested in is the one on the real axis, which is this lambda marked here. Now if you read it down off on the real axis, you can see that it does indeed match to the 1.3035, which is Conway's constant. Now what I really like about the look and say sequence is it's got a practical application of data compression. So here's an example how you would apply it for that. Here we have a binary sequence which is either white or black, and we can summarize that using the following. So you can see that we're using in total 30 characters. Now using the look and say sequence, we can compress that into the following notation: 3 whites, 7 black, 2 whites, etc. Now if you count up how many blue characters we have in that expression, there's only 13. So using the look and say sequence, we've compressed the original 30 characters down to just 13. So thanks for watching. My name's Phil, and if you're looking for an online maths tutor, you can contact me at 360 Maths. Goodbye.